Howdy and welcome back. I'd like to continue on our journey of data representation in the computer by discussing floating point numbers. I know the integral numbers took a little time, particularly when we were discussing 2's complement. I'm not going to go into as much detail when we're discussing floating point numbers. There's a couple of key takeaways that I'd like to point out, but we'll hopefully get through this with a little less time. So how we're going to encode floating point values is going to be using ones and zeros, and we're going to essentially partition out the number of bits that we have been allocated for a floating point value into 3 different fields. And when we go to interpret that memory, we will know that the underlying type is one of floating point, and we'll know that those bits have different meanings depending on where they're presenting in the sequence. But let's go ahead and begin by saying that every decimal number can be written as a power of 10 in exponential form. So we're talking here, something you all are more familiar with, perhaps easy to think about, base 10 system. This form, however, is not unique. We could write 111 as 0.111 times 10 to the third, or 1.11 times 10 to the second, 11.1 times 10 to the 1, or 11100 times 10 to the negative 2. This again, we're talking in base 10. I know I listed it out as if we were talking about binary digits. So 111, 0.11 times 10 to the third, 1.11, 11 point, so on and so forth. Okay, anyway, so yeah, this is base 10. Just recognize that we're using this to motivate normalized exponential form. Key takeaway is kind of this idea of scientific notation. The form's not unique. The numbers, we need something unique so that we can tell or differentiate between different floating point values, but having a standardized way to encode them. So we can write any non-zero decimal number uniquely as a number m multiplied by a power of 10e by ensuring that the decimal point appears directly in front of the first non-zero digit in that decimal number. This right here, this is going to be the normalized exponential form that we will be using. The number m is called the mantissa. Whoops. The exponent e, so here's the exponent. And note the difference between the definition of normalized exponential form and that of scientific notation. This normalized exponential form is normalized in the sense that we have a unique encoding scheme for these floating point values. Okay, binary numbers like decimal numbers can be written in normalized exponential form using powers of 2 opposed to that of 10. For most of this discussion, I'm going to just be speaking in kind of floating point numbers in base 10. But when we talk about the breakdown of that floating point number into its components, so the mantissa, the exponent, and then we'll get into the sign, whether or not the floating point number is negative, just understand that these numbers would be converted into binary. The normalized exponential form that you'd be seeing on screen would be binary values, which you could convert to base 10 if you wanted to. But it's going to be kind of picking and choosing these parts, and we're going to throw them into a sequence of binary digits, and then we'll have kind of a special way to interpret those digits to get us back that floating point value. So here's how we're going to store it. What I'm showing right here is going to be a 32-bit sequence, so we're looking at 4 bytes. The size, kind of doesn't matter as much as we're introducing this. It will have an impact on kind of the range of values that can be stored, obviously. But the key takeaway is that, say, your double that you're using in your C++ application, some of the other flavors of floating point numbers, such as float, they're partitioning up the ones and zeros in a binary sequence into 3 different fields. It's not like they're partitioning them in memory. It's when they go out to memory and begin reading from where that sequence of bits for, say, if you have like double D equals 7.1, we're going to go out to where that variable begins in memory, and we're going to read, in the case of double, it's 8 bytes. Here we have 4 bytes, but anyhow, we'd read from the base address all the way down, and we'd begin interpreting the sequence of bits in that. there is going to be the mantissa, which is going to be this part up here. That is going to be stored, and you're going, but there's a, period in it. How does that get encoded? Well, since we're using normalized exponential form in such that the decimal point is going to appear directly in front of the first non-zero digit in ND, well, we can kind of just treat this as assuming it's always going to be there and only encode that fractional part thereafter. So that is what's going to get put into the mantissa slot, assuming that leading 1. The exponent shown here in red is going to get stored. And again, this would all be base 2. It's just easier to think about. And base 10 is going to be stored in the exponential field. And then there will be a sign bit here, which will take on a value to communicate whether we were storing negative 7.1 or positive 7.1. So to just run through this using normalized exponential form of the value to be encoded, we can store a floating point number at a memory location, which we will think about it conceptually as being partitioned into 3 fields. In memory, it's not actually partitioned. It's all about when we go out to that address and begin interpreting it there, that the, say, C++ runtime system would go, this is a floating point number. So I need to do kind of some math here to, I have to interpret that sequence of bits according to the underlying type, and I'll know that, okay, there's going to be some first number of bits, which might be the sign bit. There's going to be another set of bits, which will store the exponent, and then there will be the mantissa, and I'll put all this together to get you your floating point number. Okay. So let's talk about that exponent, the exponent field there for a second. Few computers store E in binary form when positive or 0, and then 2's complement when negative. Others will use a bias scheme such that the exponent is calculated according to some formula. And essentially what this allows you to do is better sort positive and negative exponents if we're looking at kind of the sorting of these numbers. And then the third is going to be the mantissa, as we talked about, and it contains that fractional part of the number in normalized binary form, again, assuming that leading 1, because we can't store a period, up here. So if you have like 1.01, there's no way to get that period into, 1s and 0s. However, if we just always assume that, okay, there's a leading 1, then yeah, we only have to store that part in the mantissa. Okay, so here's a formula. I'll go ahead and say what we're introducing here is not the IEEE floating point format. This, I think, just a little bit more tangible, but the idea again is, there will be three fields in the format that your C++ program is using. It's just the formula that we're going to use to calculate the floating point value would be different because of how the standard communicates that the exponent and the mantissa are actually to be stored in memory. But using kind of the format that we're using here to get the point across and introduce the topic, you can multiply negative or raise -1 to the value stored in the sign field of the floating point number, multiply that by 2 to the exponent minus some sort of bias, which would be encoded as 2 to the n-1, subtract 1 of that result, and then multiplied by 1 plus the mantissa, 1 being that leading implied 1 using that format. Okay, so let's go ahead and look at a toy floating point number system that's going to have an exponent range of -1 to 1 and 4 bits of the mantissa. The leftmost bit of this toy floating point system will be the sign bit. We then need to be able to represent an exponent range of -1 to 1, a range of 3 values, meaning we need 2 bits for the exponent. We will then provide 4 bits for the mantissa. And again, this is just a toy example. It's meant for illustrations. It will exaggerate some of the implications of this encoding scheme. And what's to keep in mind is that the data types that you're using in your C++ application are going to have a larger range for the exponent field and a lot larger range for the mantissa field as well. But if just looking at this, we can tell that the mantissa will have an implication on the precision of the values that we can store. The exponent will get us into various different magnitudes, and then the sign, it's telling us whether or not we're dealing with a negative or positive number. So using our toy floating point number system, we could represent 3.5 with the exponent encoded with a bias and mantissa assuming a leading 1, as described on the previous slides, as following: 0, 1, 0, 1, 1, 0, 0. We can then calculate the encoded floating point value according to the formula that we presented in a previous slide, and we can see here, yes, this does represent 3.5 according to the scheme that we've introduced here. So there are some special encodings. You might see these as you're troubleshooting your applications when you have floating point values presenting in them. There are both positive and negative infinity values where the exponent is all 1 bits and the mantissa is all 0 bits. There are special not a number values where the exponent is all 1 bits and the mantissa is not all 0 bits. And there is also a positive and negative 0 values differing in the sign bit where all the other bits are 0. Okay, continuing on. It is important to note that floating point numbers are stored as only approximations. So let's just start at the smallest, not the smallest, but kind of 1 up from 0. If you were to add 1 to 0, what that number would be, and then we'll go ahead and add an additional 1 on that to show kind of that there are gaps between these floating point numbers. So we'll start out with this. We can calculate that as 0.53125 in decimal form. If we go ahead and add 1 to that, we're adding 1 and 1, so we get 0, 1, and that comes up with this representation. And we can see here that we have 0.5625. Notice there is a gap between these values. So this is going to have an implication on precision, right? Because we can't store the values that are between these two values because there's no way to encode them using the scheme that we have. If we add 1 to this value, the adjacent floating point number is going to be that. So this is why floating point numbers are only approximations. And again, keep in mind that what you're using in your C++ applications, you're going to have a lot more precision than what's being presented here. So again, notice the gap between adjacent floating point numbers increases with each power of 2. So the closer you are to 0, the smaller that gap will be. The further you are away from 0, the larger gap between the adjacent floating point values will present. And that's simply because we're dealing with this exponential system. And we're, as you're increasing in orders of magnitude by powers of 2, the gaps between, if you were to add 1 to the mantissa, it's going to be further exaggerated due to that. Okay. Floating point numbers are fundamentally precise because they represent fractional values with a finite number of bits. Therefore, at this point, it kind of makes sense that 0.15 plus 0.15 would evaluate to 0.299 repeating on my machine, because 0.15 cannot be represented exactly and is instead stored as 0.14999 repeating on my machine. Because the digits simply cut off when you get to the end of the mantissa, so the floating point numbers are not exactly represented in the computer. Therefore, a rounding scheme is typically employed to deal with this. An implication of this is that you cannot be certain that 2 floating point numbers are equal if they were calculated using arithmetic. Why? Because these imprecisions, they compound over time. The more kind of arithmetic you do, the more room for error to be introduced. So one thing that I'd typically ask at this point is to ask students to calculate the value of decimal 0.6 in binary by hand. And then I ask them, well, would you feel comfortable if your bank used floating point values to store monetary values? Well, I'll spare you the calculation. I'll go ahead and get into what I was hoping to achieve with that example, which is a terminating decimal fraction could be converted into a non-terminating binary fraction. An example is this decimal value, which is 0.1001 repeating in binary. This would indeed result in an approximation of the true value in the computer, and such conversion errors are normally small, though they can be propagated, as I mentioned, through calculations. So just to kind of assume this, illustrate this, assume a computer truncates all numerical values to 4 decimal digits. A floating point number 2/3 would therefore be represented as 0.66666 repeating. But since we only have 4 decimal digits, it's 0.6666. The relative error to this would then be 0.0001. Notice what happens when A is added to itself 6 times though. So 0.666 plus 0.66, that's going to be 1.33. And you continue this process and you can see, although we are close to the value we're looking for, we're not exactly there. And when we continually add A to itself 6 times, what we can see is that the relative error is propagated across these additions. So we were expecting, if we add 2/3 to itself 6 times, we were expecting 4, but we arrived at 3.997. This relative error is greater than that of simply representing 0.666 with those 4 decimal digits. And therefore, what we can see is as we continue to perform arithmetic, that error does increase with respect to the number of computations employed. So with that, I'm happy to move on to character data. Hopefully, that helped introduce the floating point numbers. Again, the big takeaway is where, you have a decimal value, it gets computed into, a binary value, obviously, because we can only deal with ones and zeros in our machine. And once we have those kind of ones and zeros, we're going to store that value in normalized exponential form. So if you were to go explore a double or a float or any flavor of the floating point numbers in your system, it would just be a sequence of ones and zeros, no different. But when we go to interpret that, that's where we get the actual decimal back, and how that value is interpreted by the C++ runtime system would be according to the IEEE floating point standard, which again, we've acknowledged here, though the encoding scheme that we shared with you was a bit simpler, more tangible, and hopefully illustrated the implications of this a bit easier than dealing with these big, large numbers and perhaps a bit more confusing of an encoding scheme. So with that, see you in the next video.